Now, when talking about the distribution of surface winds, the mid-latitudes, such as Saskatchewan, are characterized by westerly airflow known as the westerlies. These are winds that blow from the west to the east, while the tropics are dominated by easterly airflow called the northeast and southeast trade winds. The doldrums, on the other hand, are regions where winds are light and change direction frequently. This is bad news for sailing ships, which is where the name gets the doldrums. Kind of boring, dull, infrequent changing conditions. These are most common at north 30 degrees and south 30 degrees latitudes. One of the more famous locations, if we had the continents pasted in here, North America sitting here, would be the doldrums located off to the southeast of the United States, a place called the Sargasso Sea. In this location, the winds blow very lightly, if at all, and we get large accumulations of sargassum, a particular type of seaweed. When we put all these together latitudinally, starting at the North Pole, we see the polar high. Very little precipitation throughout the year, basically a polar desert. Moving a little bit further to the south, we get into the mid-latitudes, where we have precipitation in all seasons. This precipitation is a result of the collision of this descending cold, dense air mass to the north towards the lower latitudes, where it runs into this warm air that's working its way up from the lower latitudes. This collision results in the polar front. Fronts are where precipitation occurs. A little bit further to the south, we have wet winters and dry summers. Further to the south still, we have our subtropical high. This is generally dry in all seasons. This is a 30 degree north, 30 degree south high pressure cell that tends to persist. A little further to the south of that, we have wet summers and dry winters. Then when we get to the intertropical convergence zone, also known as the equatorial low, we have abundant precipitation in all seasons. Essentially, it rains every day or so. Now, when we look at high pressure cells in the northern hemisphere and low pressure cells in the northern hemisphere, we see an obvious difference in the way they rotate. Here we have a high pressure system where air is descending towards the screen of your computer. Ultimately, this air is going to spread away from the high in all directions. And because it is in the northern hemisphere, the Coriolis effect is going to bend that to the right. So the net result is we have a clockwise circulation of air around a high. The opposite is true for a low. The air is rising above this low at the Earth's surface. Air is pulling in from all directions to replace that rising air, and it gets deflected to the right, because it's the northern hemisphere. In this case, the resultant airflow at the surface is going to be counterclockwise. So all storm systems in the northern hemisphere are rotating counterclockwise. Storm systems in the southern hemisphere are rotating clockwise. Converting that in 3-dimension, it might be a bit more clear. Here we have convergence aloft. That air is going to descend, heat up as it's compressed, and then flow away from that high pressure cell. Again, the net surface flow is going to be clockwise for the high, and because the low is rising and the air is coming in to replace it, the net airflow at the surface is going to be counterclockwise for the low. When we look at a more extreme example of cyclonic flow, again, in the northern hemisphere, the flow is going to result in counterclockwise circulation. In this case, we have a very large storm that developed just recently, Hurricane Laura. This uplift associated here with the hurricane is going to result in air streaming in and being deflected to the right. Air streaming in, deflected to the right. Streaming in, deflected to the right. Therefore, counterclockwise circulation. Now, this starts out as a tropical wave. A tropical wave is a type of atmospheric trough, an elongated area of relatively low air pressure, oriented north and south. And this is going to move from the east to the west in the tropics to the north of the intertropical convergence zone. and it's going to result in areas of cloudiness and thunderstorms initially. If it develops further, we might see a tropical depression form. A tropical depression is a tropical cyclone that has maximum sustained surface winds. That means winds that last for more than a minute of over 38 miles an hour. This converts to 33 knots. A tropical storm is a tropical cyclone that has a maximum sustained surface wind, again, a 1 minute average, ranging from 39 to 73 miles per hour, or 34 to 63 knots. Here we have an image from August 20th that shows a new wave developing off the coast of Africa. This is where our hurricanes start, generally, off the coast of Africa here. This wave is going to move across the Atlantic, where it may strengthen and become a tropical depression. Here we have two tropical depressions in play, Tropical Depression 13 and Tropical Depression 14. These hurricanes, again, commonly develop off the coast of Africa. The Azores are located here. There's a standing high pressure cell called the Azore High that sits out here. Storms don't form here, they form to the south. And because of this high that's rotating like this, the storms are driven to the west. They're going to continue to go west until they run into the Caribbean. These land masses here, these big islands, coupled with the peninsula of Florida, are going to steer these hurricanes generally to the north. Sometimes they break on through the Antilles here and do some damage in the Gulf of Mexico. This is where hurricanes typically develop in the Atlantic. This is where they typically develop in the Pacific. If we move into the Indian Ocean, we call these types of storms cyclones. If we move into the Western Pacific, they're called typhoons. And here off the coast of Australia, they're called willies. Here we can see historic storm tracks. Again, there's a persistence in the track of most of these storms. Some variability that causes us problems in predicting exactly where landfall is going to be made, exactly where the damage is going to occur. But nonetheless, they tend to follow consistent paths. More consistent here and here than in the Atlantic. And that's unfortunate for people that live along the Gulf Coast here, the East Coast, the eastern seaboard of the United States, and maritime Canada here. Now, what's going on internally when a hurricane develops? We have warm, humid air. Again, is warm, causing lower density. It's humid, causing lower density. That air is unstable, so it wants to rise up. And it's going to rise up here in these bands of high-speed winds. The faster it rises, the higher the wind speed at the surface. So we see the development, ultimately, of a well-formed eye wall, where air is rising very rapidly. It's because it's rising rapidly, it's cooling rapidly, and it's dropping enormous amounts of precipitation from these eye wall bands. When it drops that precipitation, latent heat is given off, and that further fuels the rising of these air masses. We'll notice as you move away from the eye wall, there are additional rain bands. Here we see a three-dimensional depiction of that. So again, we have air rising rapidly in the eye wall. That's causing counterclockwise spin in the northern hemisphere. Ultimately, the inflow of air is going to provide additional moisture and additional heat. So as long as this storm is over warm water and has a supply of humidity, of moisture, it's going to continue to develop. Once it reaches land, that energy gets cut off. And we can see that depicted here in terms of air pressure. The lower the air pressure, the stronger the winds. You'll notice that the low point of air pressure here at the surface coincides with the high point of winds at the surface. So the highest winds are going to be located just adjacent to the lowest part of the low. But there's more to a hurricane than that. It's not just wind that provides a danger and provides a potential for damage. The main concern is not the wind, is the wind-driven surge. In this case, high-speed winds are grabbing onto the surface of the ocean and pushing that ocean ahead of the storm. Coupled with that push, that physical dragging of the surface of the ocean into this pile, we have the reduction of air pressure. As air pressure is reduced beneath the hurricane, it's going to cause the ocean to rise in response. So we have a pressure-driven surge that's about 5% of the total surge superimposed upon the wind-driven surge here. Because this is reaching shallower and shallower water, these waves get piled up higher and higher. Much like a tsunami can't be observed out in the open Pacific, once it reaches shore, that wave gets shortened very rapidly. And when you shorten that broad, large wave, it gets taller. And that's what does the damage. Same thing in a hurricane. This broad pile of water gets shortened and heightened as the water gets shallower. When we talk about anticyclonic flow, this is air flowing out of a high pressure region, again curving towards the right in the north, ultimately resulting in clockwise flow. This anticyclonic flow is going to run into warm air here in the southeast and central portion, the Midwest of the United States. When an extratropical cyclone, a cyclone that develops outside of the tropics, moves to the south, it results in this collision. Now we can take a look at this collision three-dimensionally here. We have the cold front here, cold polar air coming out of Canada, Canada's gift to the United States. This air is going to bulldoze south, and it's going to scoop up and displace any warm air that is lower density as it moves to the south. So we have a precipitation front here associated with this cold front. These triangular symbols represent cold air sliding under warm air, whereas these rounded hemispherical red blobs here represent a warm front. In this case, the warm front is riding up over cold air. So cold air here, or cool air in this map, cold air here, cold air is sliding underneath warm air here. The warm air is riding up over cool air here. In both instances, we have precipitation along these fronts. Precipitation here, precipitation here. This is what you're looking for in a weather report. Now, when we go to upper airflow, at equal altitudes in the atmosphere, the pressure will be lower to the north, and this initiates flow along that pressure gradient to the higher latitudes. The thickness of the troposphere and the tropopause is going to change with latitude. At the equator, the atmosphere is much thicker than it is at the higher latitudes. Now we can put in millibar heights of air pressure, and you'll notice those millibar heights differ from place to place. They're lower at the high latitudes than they are at the low latitudes. This results in a tilted tropopause. This tilt in the tropopause is in turn going to be influenced by the Coriolis effect. So this high altitude flow is going to be curved to the right in the northern hemisphere. And this becomes the jet streams, belts of high-speed wind that circle the Earth at the position of the greatest temperature pressure gradient. Therefore, that's where the action is going to be. We call this flow a geostrophic wind, airflow that's generated by a balance between the pressure gradient and the Coriolis effect. Airflow is thus to the right of the pressure gradient force. Air wants to move from this position, high pressure, to this position, low pressure. It's influenced by the Coriolis effect to curve it to the right. As it's curving to the right, it still wants to go this way, but the Coriolis effect is still acting on it. So no matter how hard it wants to go to this low pressure cell, it gets deflected, bent to the right. Wind flowing perpendicular to this pressure gradient force, being curved to the right by the Coriolis effect, means that this Coriolis effect is going to become more effective as the flow becomes greater. Eventually, there's going to be a balance between these two, the pressure gradient force and the Coriolis effect. And when they're balanced, that is going to be the pathway of the air parcel. That's going to be the position of the jet stream. Now, we talked about isobars before. These are lines connecting equal places of pressure on a map. We also mentioned Rossby waves. Rossby waves are ridges and troughs in upper atmospheric airflow. These ridges and troughs are going to determine or dictate the movement of high and low pressure systems. A typical position of the northern hemispheric geopotential height of the 300 millibar surface is depicted here. So this would be a trough in a Rossby wave. This would be a trough in a Rossby wave. This would be a ridge. This would be a ridge. Not much of a ridge in either location, but a ridge nonetheless. And big trough here. So ridge, trough. Okay, now we're going to take a look at the jet stream, how the jet stream evolves. And the animation here, what you'll see is this undulating amoeba-like mass of cold air at the high latitudes, looking down directly upon the North Pole. A ridge forming here, a ridge here, trough here. Which brings us to seasonal variability in insolation. Obliquity is the tilt of the Earth's axis relative to the plane of the planet's orbit around the Sun. The Earth is generally tilted at about 23.5 degrees from the perpendicular, and we say that obliquity is the reason for the seasons, this tilt away from the vertical. If the Earth was oriented vertically with the axis of rotation perpendicular to this path, this orbital path around the Sun, we wouldn't have seasons. But it's tilted, so different places on the Earth receive different amounts of insolation at different times of the year. All right, let's take a ride around the Sun. Now you notice the Earth is tilted at approximately 21.5 to 24.5 degrees relative to the perpendicular. As a result, as we travel around the Sun, we're going to see different portions of the Earth illuminated to a different degree. Now, at December, the very end of the year, zoom in a little more closely here. At December 21st, the Northern Hemisphere receives the minimal amount of insolation during any given year. And you'll notice here, this red line, this red circle represents the Arctic Circle. This is the portion of the Earth that is at least once a year in complete darkness. So everything above that circle, that red circle, 66.6 degrees north latitude, experiences at least one full day of 24 hours of darkness. We're going to run this forward. And we're approaching spring again. At the spring equinox, our days are precisely 12 hours long. Therefore, nights are also precisely 12 hours long. Now we're going to run that forward again, starting in March, until we get to June 21st. At June 21st, you'll notice that that red circle, the Arctic Circle in the Northern Hemisphere, is exposed to light 24 hours a day. So every position above that red line is going to experience at least one day of 24 hours of continuous daylight. Again, approaching our current time here. The end of September, near the end of September, we're going to experience exactly 12 hours of daylight and exactly 12 hours of darkness per day. Now, if we throw in the Earth's profile, you'll see that that is correct. The vertical rays of the sun striking the equator, all locations on Earth experience 12 hours of daylight, 12 hours of darkness. This happens September 22nd this year, sometimes the 21st. We have an equinox again in the spring, March 21st, March 22nd, where the days are exactly 12 and 12. Moving towards winter, we're going to experience less and less daylight. Until we reach the dark times. The end of December, the darkest time of the year here, we only have, a few hours of daylight. Most of our 24-hour period is darkness, doom and gloom. Again, we'll throw in the Earth profile here, and we can see that we're receiving 12 hours of daylight at the equator. We're receiving 24 hours of darkness north of the Arctic Circle. And we'll just let that run with the Earth profile to give you a feel for how that orientation, that tilt of the Earth, influences the amount of light we receive at any given time as the Earth revolves around the sun. And we could just let this go forever. Just like in the solar system. Hardly ever really catching it. It moves to the north in response to the seasonal changes in insolation. This gives the tropics and subtropics distinctive rainy seasons. If it passes twice in a year, there's 2 rainy seasons. If it passes once in a year, 1 rainy season. Panama has 2 rainy seasons a year. Northwestern Costa Rica, really 1. Mexico has 1 rainy season because the intertropical convergence zone doesn't pass southern Mexico twice a year. It moves up to southern Mexico, then it moves back to the south again.